Hi, hello everyone. My name is Sudhanva Puranik. I am a content author at I Get It Tata Technologies. In today's session, I am going to cover a topic how to convert a fully constrained assembly to mechanism connections using Creo Parametric 9.0. So in this session, I will be covering following topics: the need of converting assembly constraints to mechanism connections, methods of assembly constraints conversion, dealing with connection sets at sub-assembly level, and finally an overview of the completed assembly after converting constraints into mechanism connections. So to begin with, the first thing which I will discuss about the need of converting assembly constraints into mechanism connections. It's a common practice that initially when we do some product design, so there is a fully constrained assembly, and then after having the final assembly, we need to check the feasibility of the assembled components so that they can achieve the desired motion or not, that we need to check. And after having that desired motion, we can check for the packaging like motion envelopes or trace curves or any measures to be evaluated. That kind of a further overview of the analysis results we can achieve. So based on this need, we have a different methods of assembly constraints conversion, like first method of releasing any required degree of freedom and then converting the assembly constraints to mechanism connections. That is the first method. And second one is about completely recreating the sub-assembly directly by using the mechanism connections only instead of assembly constraints. Then further, when we have the sub-assemblies, then the sub-assemblies, they connect with two different components from the main top level assembly. So in this scenario, we need to address this by dealing with different connection sets at a sub-assembly level. So after covering these three major topics, at the end of the session, I will focus on a complete overview of the entire top level assembly, where I will have converted all the constraints into mechanism connections. So I will show over there a brief kinematic simulation overview. So with this, let's start and let's look at this into PTC Creo 9.0. So here I'm having this hydraulic crane assembly, and you can see the model tree wherein all the components, they have been fully constrained, and as per the need of the assembly or as per the need of the mechanism as well, the first component, that is the grounded body, and that has to be connected with the default constraint. So that's the basic requirement that is already available, and that's nothing but this base plate part. Now further, there is one foundation, and in real life the foundation has to be bolted to the base plate by using these 4 bolts. So in the context of mechanism, the base plate is a true grounded body, and the foundation and 4 bolts, they are supposed to be rigidly held together along with the base plate. That's why there has to be a rigid connection between foundation and base plate, and further between bolts and foundation. So if I look at the foundation.prt, then you can see that it is having currently only one single constraint, that is the coordinate system to coordinate system matching is available. And now to go for a mechanism application, instead of a fully constrained component, we should convert it to the required connection, that is nothing but the rigid connection. So that is immediately activated from the connection types drop down menu. Now further with the bolts, so there is a pattern of bolts, and I can deal with the first instance, the parent of the pattern. Now we can look at these constraints like the bolt shaft and the hole over there, the centers are matching. Then there is a matching between flat face of bolt head and top flat face of the foundation, and then there is one parallel constraint that is available between one plane from the bolt, that is the front plane, and with the similar kind of a parallel surface, so that has to be this surface. So and it has to be the parallel constraint. So in this way this is fully constrained, the bolt.prt, and we can just convert this constraint, all the three constraints, to the rigid connection. So that way we can now check that the three components, base plate, foundation and bolts, they have to be the one single body in the context of mechanism that has to be said as a ground body. So if I now look at the mechanism application, and if I look at the rigid bodies, it should show me that the ground body is nothing but the base plate, and further the other bodies, they will be, yeah, so it has to be in the ground body. So ground body, it shows me the base plate plus foundation plus pattern of 4 bolts. And further, as I populate the mechanism further, it will show me appropriate list of bodies that we will further see into the final assembly. So now after having this done with the first 3 components, so now let us deal with the rotary attachment. So this is nothing but a yellow part, and as the name is suggesting, this part is supposed to rotate about the axis of this hole in the foundation. So if I now edit the definition of this rotary attachment, it is currently fully constrained, and there is one coincidence constraint with the hole, and second one is the mate, flat face mating constraint is there. So then there is a one normal constraint which is between this surface and this surface, one surface from rotary attachment and one is from foundation. So let me delete this constraint, and now after having that deleted, if I now disable this allow assumptions, then the 3D dragger, that will show us 1 degree of freedom allowed, that is nothing but the rotation about the vertical axis, and the status is currently partially constrained. So when it is a partially constrained, when I am releasing 1 degree of freedom over here, then I have the drop down wherein it is showing me the possible connections. So as I know, it has to rotate about the vertical axis, so for that I will go for the pin connection, and this way I have converted the 2 constraints to the equivalent mechanism connection. So the first coincident for the axial mating, that has been listed under the axis alignment, and for the translation locking I am having the flat surface mating type of constraint. So this is not done yet, because since it is having the rotation, so I need to define the limits of rotation as well. So for that I can click on this rotation axis, and I should select the 0 references from both the components. So the 0 reference from rotary attachment would be this surface, and similar reference from the assembly side from the foundation.prt, that is this surface. So currently they are having 90 degree as the angle, minus 90, that is just a direction indication, but this I want as my reference position, this minus 90, this I want as my 0 position. So let me just click on this set 0 position. So it's now set as 0. The angle 90 between these 2 surfaces, that has been set as a 0 position. So I will enable this regeneration value by clicking this option, and then I would have to set the limits of motion. So I can say that it will rotate by a 90 degree in both the plus and minus direction. So let us say first limit as minus 90 degrees and second limit as plus 90 degrees. So that way I have converted the rotary attachment as well to the mechanism connection, which is a pin type mechanism connection. So now for the rotary attachment, you can see this icon over here, rectangle inside which there is a dot. That's nothing but the packaged component. Packaged component means it is having a mechanism connection. It is not fully constrained. It is allowed with at least 1 degree of freedom as free. That is the indication by this icon over here. So now further I can do it for the arm pin. The arm pin, it is a component which is held with this rotary attachment in a rigid manner, so that the rotary attachment and the arm pin, they are said to be kind of a one single mechanism body, and that's why this moving arm that will rotate about the arm pin. So again for the arm pin I can edit the definition, and you can see that it is having 3 constraints already defined. So I will just convert that to the rigid connection. And now further for the moving arm, if we look at that moving arm, it's currently fully constrained using assumptions. That's why I would disable the allow assumptions and I would convert this to the pin connection. And for this moving arm, I will not deal with the rotation axis, the motion limits, because the moving arm will not rotate on its own. It's not having kind of a prime mover. It will be rotated based on the slider connection over here. There is nothing but the piston cylinder arrangement. So this much is sufficient for this moving arm, and I would complete the constraint conversion to connections for the moving arm as well. Now let us deal with the moving arm hydraulics, that is the sub assembly. It is containing moving arm cylinder and moving arm piston, the 2 components. So to deal with this, let me open this in a separate window, and here now I will try to do it in a different way. So here, instead of releasing the degree of freedom and then trying to convert the constraints to connections, here I will just delete all the existing constraints which are there available. Then let me enable the plain display, and I will just take it out from this hole somewhere here. So now instead of starting with the constraints, I will start with the connection only. We know that the piston will move inside the hole of the cylinder, so that is nothing but a linear motion that will be dealt with the slider connection. So I am starting with the slider connection, and for the axial alignment I will go for the 2 round surfaces from both the components. Then since it is releasing the kind of a linear degree of freedom, so it will lock the rotation. That's why the rotation definition is available. So for that I will match these 2 rotation reference planes from both the components, and this way the connection definition is established. Now since it will be sliding inside the hole, so I need the translation limit to be defined. So for translation axis limits, I will first select this surface from the piston, and secondly the limit plane from the cylinder. So the current distance is something 523. Let me make it 0 first. That I will set as a 0 position. Then I am just ensuring that the connection axis is moving out. So that's what I want. From the 0 position it should move out. So the direction is well, and I will just set it as regeneration value for the 0 position, and minimum limit I would say as 0. The max limit I would say as 40 mm. So this way I am completing the definition of this moving arm hydraulics. Now let us move again to the main assembly. So now for moving arm hydraulics, I will have to change the definition as well with respect to the top level assembly. So here we are speaking about the next point, that is nothing but the dealing with connection sets at subassembly level. So let me first delete all these constraints which are available for this moving arm hydraulics, and further I will take it somewhere here. Now uh, this pin from the cylinder of moving arm, it has to rotate inside this hole, so it has to be with a pin connection. So for axial alignment I would match this surface with this whole surface, and for translation I would match this surface with the inside surface of that yellow part, this surface. So that way I have got the constraint created for the translation, and in that way I have got the pin connection. So it is supposed to rotate about this hole, but then the question comes that what about the connectivity between this pin and this hole? So for this case I would have to go to the new set, and now at this hole location, instead of having a pin connection, I would go for a cylinder connection, because it has 2 degrees of freedom, one translation and one rotation. So that's why we have to define over here only the axis alignment. So let me choose this surface and the whole surface over here. That way I have got the connection definition complete for the moving arm hydraulics. So this was the main kind of a topic which we should look into. So here I have covered most of the things till now. Like first I have explained what is the need of converting assembly constraint to mechanism connections. Everyone must have understood that because we had the initially fully constrained assembly, and ideally this assembly, it's a crane, so it has to move. It is having one piston cylinder arrangement over here that would rotate this moving arm, the second piston cylinder arrangement that would rotate this lifting arm, and the third piston cylinder arrangement that will try to rotate the hook. That's why this assembly has to have the motion, and that's why we have understood the need of converting the assembly constraints to mechanism connections. Then further we have seen both the approaches. In the case of rotary attachment, I tried to release the required degree of freedom of rotation, and then I tried to convert the assembly constraint to the pin connection. And in case of moving arm hydraulics subassembly, I tried to recreate the subassembly directly by using the slider connection. So after looking at those two things, now further I have also shown you how to deal with the connection sets at subassembly level. Over here for the moving arm hydraulics, I have shown you how I have tried to create 2 connection sets. One is pin over here and one is cylinder over here. Since it is a subassembly, so it is connecting with the yellow part and the red part. So with each part it will have the different sets of connections. So so here now what happens, that same kind of a piston cylinder arrangement is available over here and over here. Also the arm pin what we have seen over here, same arm pin I am having over here also. So with respect to this arm pin, I can create the pin connection for this lifting arm, and for the lifting arm hydraulics I can again convert it to the slider connection having proper motion limits, and same I can do with the hook hydraulics, wherein this same kind of a slider connection I will have between hook cylinder this part and hook piston this part. So here something more we can see at the subassembly level. So at the hook hydraulics subassembly, for this hook piston you can check that it is having already the slider connection, and now I should deal with the hook. So now let me just delete this centered constraint and let me take the hook out somewhere here. So we can see that it is having a spherical surface over here and spherical similar kind of a cutout over here in the hook piston. So the hook has to have a ball joint over there. So for that I will go for a ball joint, and I will just select the points from both the components. So I'm having the points. We can check the point names as well. So both the points, they are available. Let me just choose this point with this point, and I have got the ball joint created. And further I can deal with the cone axis. So for cone axis, I can deal with the axis from both the parts. One axis, that is from this part, and again this cone axis definition is optional. Even if I don't create it, still it will work in the main assembly. So due to the time constraint, I will not deal with the cone axis creation, and let me just complete this definition over here only. And that way this hook hydraulics assembly has been created. And further with this assembly, I will again delete the constraints what are available over there. Let me put it somewhere here, and again I will have two connections. One is the pin connection for this pin with this hole, and the surface mating over here, and I will have a new set. So in the new set, I will go for the cylinder, and let me choose this surface with this surface. So that way the connection definition has been complete. So this way the assembly was initially fully constrained, and I can convert it very quickly to the mechanism connections. So now let us look at this complete assembly, this hydraulic crane final. I am into the mechanism application, and here you can look at the bodies basically. So in the mechanism bodies, you can look at the ground, and for the body contents of ground body, I am having only the base plate, foundation and bolts. So these three components, or rather 4 plus 2, 6 components, they constitute one single ground body. Then the second body, that is nothing but the moving arm piston, because the second body, moving arm piston, that is only supposed to translate. So each of the body definition has been well established. The lifting arm piston, further the body 3, that has to be the hook piston, this piston over here. Then the body 4, that has to be the hook which is supposed to rotate separately. Then the body 5, that's nothing but the rotary attachment along with the arm pin, because we know that this arm pin over here, that is a kind of a rigid body connected to the rotary attachment. So the bodies over here, they are listing the proper mechanism body definitions, and we are having 10 bodies, but ideally the components are 14. That way the mechanism has been established. So here I have further created some motors which are defining the motions of moving arm, lifting arm, the hook and crane. So by using all those motors, I have created one kinematic mechanism, and for each of the motor I am defining appropriate sequence and appropriate start and end times. So after defining this, I can run the analysis which I have already run, and we can check the playback. So if I look at the playback of this crane motion, so with some half speed, so the moving arm goes down, then the lifting arm goes down, then the hook goes inside, that will lift the load. Again lifting arm and moving arm, they move up, then they move 90 degrees. On that side the load has been taken down. Again the lifting arm and moving arm, they come up, and then the whole crane rotates by the 180 degrees. That way the motion has been established. So whatever the motion is available in reality, that I have simulated over here, and by using this motion I can achieve different outputs like the measures, or the other one that's nothing but the motion envelope or the trace curves likewise. So this is a brief intro about this mechanism. And in our I get it, if you look at this catalog of I get it, in the PTC Creo catalog, in the PTC Creo 4 subcategory, I am having this detailed course about mechanism design using Creo Parametric 4.0. This will be released soon, and you will understand each and every aspects of kinematic mechanism design over here. So I request you that please go through the I get it and try to purchase this course. This will definitely increase your knowledge about the mechanism design using Creo Parametric. Also, please do visit this I get it learning for engineers page on YouTube. Here we are having different playlists. So the PTC Creo, that is mine playlist. Apart from that, there are we are having different authors who are creating different type of playlists like Katia or GD&T, Siemens PLM, SolidWorks, and so on. So stay tuned to I get it YouTube page. Also try to purchase the courses and make the most of our I get it knowledge base. Thank you.